Hello everyone and welcome to the 17th lecture of the course Advanced Structural Analysis. We have been discussing the generalized flexibility method in the previous session. We have discussed the concept of the member flexibility, and with this system we will try to understand the structural system, which is the overall action forces in the structural system. We will also try to make the connections between the structural and the member action forces system, and that we will try to add through the action transformation matrix in the given problem. So, as we have already seen in the previous case, we considered that our intention is that somewhere we can define the flexibility matrix for the individual members, which could be defined in a much more generalized manner and which will be always standard values associated with the individual systems. And now we come up to the structural system and we look at the structural system, that what really we have as an information which need to be translated into the member action force system of the given problem. So, when we consider the action forces on the structural system, which means that original problem which was given to us, out of that we considered that all the loads are active only at the joints of the given problem, and with that idea we were able to convert the given problem into a system like this, where we have now a system of the redundant which is active at one of the positions, system of the joint forces which are active in the direction of the respective AJ1 to AJ4. Any of these forces could be 0 as well because of the external load not active in those directions, but the general idea is that in a simple conditions we can have possibility of these all joint action forces in the given problem. Now, if I consider a simple determinate problem of the given member, these are the forces, the joint action forces AJ1 to AJ4 and the redundant 4 AR1, which are primarily responsible for any possible deformations in this given member. We have also a contribution of the load which is going to the respective joints of the given system which are already restrained, and they will become the part of the external support reactions of the given system. So, we understand if the system is already restrained with respect to this particular joint, these two forces are not going to make any contributions to the deformation of the given member. And with this idea, we say that the structural action forces will be typically introduced with respect to the redundant force which is AR1 in the given problem, and at the same time the joint action forces of the given system which are AJ1 to AJ4 in the given problem. As we have identified that these are the action forces for the structural system, now we can consider that corresponding to these action forces we can define the generalized flexibility of the given structural system. As we move ahead with the given system, we understand that the given system of the structural forces of the overall system can now be considered with respect to some connection of the member action forces as well. We will now try to see some of those content. Now, as a simple case, we will try to solve one problem in which we want to identify the set of structural action forces. Say this is the original problem which is given to us, in which the given system is subjected to some member loads. We have considered that as per the initial idea that we want to convert all the forces as a equivalent joint load. So, the given load which is of the 5 kilonewton meter has been converted into the equivalent joint load. So, the overall length of the given member, say if you define as 12 meters. So, corresponding to that the amount of the given reaction can be identified here, which is of 30 kilonewton. At the second end also it is 30 kilonewton of the given system. So, these are the two end reactions or end forces which we will get as the equivalent joint loads of the given system. We have already discussed earlier the procedure to get these action or the equivalent joint loads. We restrained all the degrees of freedom and we convert the equivalent loads as the fixed end reactions of the given problem. The amount of the fixed end reactions which we have obtained, we just reverse their roles or we reverse their directions and provide it on the originally existing system, and that becomes the equivalent joint load of the given problem. So, this is how we have defined this 30 kilonewton over here as the equivalent joint load in the vertical direction. Corresponding to this moment of the 60, we have provided here the moment again in the opposite direction of the 60 amount, but we have also an active moment of 20 kilonewton on the given system. So, we added the contribution due to that, and that is where it becomes a combined load system of the given problem. At the same time, we understand that at the joint B of the given problem. So, if I say that this is joint A, this is B and this is C, at the joint B of the given system we have a vertical load of 30 kilonewton, we have a moment of 60 plus the active moment on the given system, which is of 15. So, we add the reverse of this moment, which is in the anti-clockwise direction, plus the 15 kilonewton meter, which is also in the anti-clockwise. That makes a total moment of 75 kilonewton meter active there in the given problem. And then we have finally the member BC, in which there is no active load defined, and that is why we will not be getting any contributions of the reactions or the joint loads on this given problem. Now, as an idea of the given problem, we understand that the given system can be considered with the redundants AR1 and AR2, which are the two redundants of the given problem. I can consider now a determinate problem, which is a problem like this, and this problem will be undergoing any possible deformations due to the nature of these two redundant forces, as well as the joint action forces active on the given problem. And now, what joint action forces I must be considering? With respect to the joint A, I have already considered AR1 and AR2 as the redundants. So, there is only one possibility of the available joint action force there, and that is AJ1 for the given system, which is the moment at the joint A. At the similar point, joint B of the given problem is not provided with any support conditions. It has possibility of the rotation at this point, and this becomes my second possibility AJ2 of the given system. Now, with respect to these two criteria of the given system, we can have now AJ1 and AJ2 as the possible two set of the action of the given joint system. We have actually considered the third one, which is corresponding to the transverse movement of the given system. So, I will consider this one as the AJ2, and the rotation will be considered as a AJ3 for the given system. So, considering these three action forces in the given system with respect to the joint and two action forces with respect to the redundant contributions, now we identify that there are total 5 number of forces which are active on the given system and which are responsible for any kind of deformation taking place in the given problem. One must again understand that the values of the AJ2, AJ3 all are defined corresponding to active loads on the given problem. We understand that at the joint 2 or at the joint B, in this problem there is an active load of 30, there is a moment of 75. So, I have to consider the corresponding AJ2 and AJ3 in the given directions, because those are the one which are responsible for making any possible deformation in this determinate system. So, as a structural system, now we define the structural system has AR1 and AR2 as the two redundant parts, and AJ1 to AJ3 as the three action forces of the given joints. As a definition of the given problem which we have identified, we can give their values also. AJ1 for the given problem, if we locate, is the amount of the moment at the given joint A. The direction which we consider as a positive sign convention is anti-clockwise, whereas the moment over here is clockwise. So, I consider AJ1 equal to minus 40 in the given problem. With respect to the AJ2, I understand that there is a force in the direction downward in the given problem. We have considered AJ2 in the positive y coordinate in the given system. So, AJ2 also becomes minus of 30 in the given problem. And finally, we have AJ3, which is anti-clockwise in the given problem. We have an anti-clockwise moment at the joint B. So, we can define AJ3 as 75 kilonewton meter in the given problem. So, having these three values, we can understand that action forces of the given problem are identified, in which now the given problem is subjected to the two redundants AR1 and AR2, and respective to the given system, we have these joint forces which are AJ1 to AJ3, and these are all responsible for any set of changes or deformations of this given determinate system. Now, as a next case, we try to make the connections between the structural system which we have identified and the system which we have considered as a member action force in the given system. So, we have considered this problem as one example. I will again revert back to the same original problem which we were initially discussing, which is the original problem over here. So, we have for this problem also AR1 as a one of the redundant and AJ1 to AJ4 as the 4 joint action forces of the given system. So, with this idea in mind, if I consider this problem, we have these set of forces which are the structural action forces, and we have at the same time the two member components, member 1 and member 2, which are independently defined as per the original configuration of the given system, but they are not connected with each other, and we have identified the 3 number of member action forces in both of these members. Now, I need to connect, can we give the values of these AM1 to AM6, which are the member forces, in terms of the joint or the structural action forces of the given system. So, in order to do so, we can analyze the determinate system, because these are all the determinate system of the given problem. We can analyze this determinate system for the unit load in the direction of the structural action forces. I can apply the unit load corresponding to this. I can apply the unit load corresponding to the individual joint action forces on the given system, and with respect to each of these structural action forces, including both the joint loads as well as the action because of the redundant part, we define the corresponding values of the forces in the direction of these member forces. So, which means that when I consider, say, with respect to AR1, I have this as a simple determinate problem. I apply the unit load over here, and corresponding to this unit load, I will just try to draw a simple free body diagram of the given system and evaluate that what are the forces which are appearing at the ends of the given system for member 1 and member 2. The values of these forces will be the respective values of the member action forces when we have applied the unit load in the direction of the redundant action force of the given system. So, in this manner, we now start with first the redundant action force. As we said, we apply the unit load in the direction of the redundant one, and we consider corresponding to this given system a free body diagram can be identified, in which there is a load of 1 unit applied over here. Corresponding to that, I get the opposite 1 unit load at the downward part. The moment due to this part will be 1 into L, which is the length of this given member. Equal and opposite moment will be identified at the second end to make the equilibrium of this given system. So, this is our member 1, member 2 of the given system. Similarly, for the member 1, we will just transfer the equal and opposite loads. So, the moment L kilonewton meter has been transferred, the vertical force which is downward over here will be transferred over here. So, it is 1 in the upward direction. There is no other active load on this given system. So, I just define the equal and opposite values over here. But we understand after this whole calculation that corresponding to the values of AM1 to AM6, which were our intention to initially define, we have now got the 2 member components individually defined, and corresponding to this structural action force which we have defined with respect to the redundant one, I have now calculated their values. I will say that AM1, and we can just reflect back on the original problem that this is the value of AM1, this is AM2, this is AM3, and similarly AM4 to AM6 in the given problem. So, now I can define their values individually. AM1, which is again in the direction of the the positive coordinate, will be defined as 1 unit. AM2, which is the force over here, is not active in this given system. So, it is 0 for the given problem. AM3, which is the moment in the same anti-clockwise direction, is the L unit for the given problem. Now, we go to the member 2. At the far end of the given system, we have one force which is in the vertical direction, but we have no force in the horizontal or moment force active on the given system. So, we define that the value of the horizontal force is 0, vertical is 1, and the moment value is 0. So, these become the corresponding member action forces when I apply the unit amount of the force in the structural direction with respect to the redundant. So, one of the structural redundant force has been applied in the statically determinate system, and corresponding to that I have calculated a simple free body diagram, and once I do it, I have now got the connection between the member system and the structural system of the given problem. Now, originally for the member system, we have identified that the flexibility coefficients are known to us. Now, we have also calculated that how the structural system will be connected to the member system for individual loadings. In the similar manner, one can also now do the similar process for AJ1, AJ2, AJ3 of the given problem, which means that for all the joint forces, and AJ4 as well, for all the joint forces which are active in the given problem, one by one we start applying the unit load, and corresponding to that we draw the free body diagram of the given member systems and evaluate the forces in the direction of AM1 to AM6. So, the members which were initially considered to be fully independent have now been considered to be attached to each other with respect to a defined force in the direction of the structural system, and this connects the given system with respect to the structural and the member system of the given problem. So, over here we bring the AJ1 in the given problem, AJ2 in the given problem, AJ3 and AJ4 in the given problem. Individual to these cases, we apply the similar set of forces in the given problem, and we calculate the free body diagrams of the given system, and our intention is to calculate the forces in the direction of the individual AM1 to AM6 components of the given system. as we evaluate all these components of the given system, we write them into this standard form, where all these forces which are being calculated with respect to unit load application in the given system will actually be multiplied by the actual value of the load active in the direction of the structural system. And that is where we connect this given system, and we call it as that this is the action transformation matrix, and this matrix we call as B of MS, because it is connecting the member system to the structural system of the given problem. Somewhere while doing this calculation, we understand that we have balanced the equilibrium of the given system. So, this member as a determinate system is subjected to one load in the direction of AJ1. As I draw the free body diagram for it, we will be writing the equilibrium of the individual members. So, the action transformation matrix which we are enabling here is actually the conditions of the equilibrium in the given system. And once we define those conditions of the equilibrium, we can define these action transformation matrices of the given system. We will briefly see some components of the given system, and the remaining ones can be obtained later on. So, as we define this part, we have defined already with respect to AR1 the given system. So, I just define the values in the similar manner with the AR1 over here. With respect to AJ1, if we describe, we have a load which is active over here. If I draw the member 2 of the given system, as this member is not subjected to any load, so there will be no load which will be active in these directions. At the same time, when I come to the given member over here, this will be having a load of 1 unit at this position, equal and opposite reaction will be provided over here, and along with that it will also get a moment reaction which will be provided with respect to the height of the given member. So, this will be defined as a H value. So, at the position of the given loads which are in the direction of AM1 to AM6, I calculate the values of the individual components. AM1 is 0, AM2 is -1, AM3 is 0, AM4, AM6, AM5 and AM6 all values are 0 corresponding to AJ1 system. We now move to the AJ2, which is again in this case, again we understand that member 2 is not subjected to any load. So, it will not be provided with any of the amount of forces over here, all these values are 0, whereas in the member 1 we consider that it is having one load in the vertical direction, equal and opposite force will be active over here, and no moments or other forces will be available. So, that is why we define AJ2 having AM1 component 1 and remaining all the components being 0 in the given problem. So, identifying these systems are not very complicated, but only thing we may now realize that doing this for a more complex problem is a time taking procedure, and it does not have a very standardized system because the choice of the redundants are not unique. A user can also go with a different choice of the redundants in the problem, and accordingly the whole problem may have a different solutions or different way of the solution scheme in the given problem. So, that is why the implementation of this kind of an approach for a computing environment is not very much suitable. But as far as the implementation for a manual understanding and the generalization of the flexibility matrix is concerned, we see that now in the similar manner as we have defined the action forces of the given system in terms of the structural action forces, we can write them as simple A of m is equal to B of ms into A of s, where A of m is the member action forces of the given system, A of s is the structural action forces of the given system, and B of ms is the action transformation matrix of the given system. So, we define this as action transformation matrix for the given system. In the same manner, now we can also understand that as we are applying the unit forces in the direction of each of these structural action forces, I can also keep on calculating the reactions which are being generated at the ends of all of these members or all of these supports of the given problem, and those will be helpful for us when we want to evaluate the reactions of the overall system, because we have already seen the procedure of the matrix analysis in which we want to parallelly evaluate the reactions of the given system as well. So, we define the system of the reaction transformation matrix, which typically evaluates the reactions of the given system. In this given case, we have the system having 3 reactions. So, we have 1, 2 and 3, these 3 reactions identified in the given problem. So, corresponding to the all these components of the action forces of the given system, one can identify a standard matrix which will be described with respect to all the action forces, say A of R1, A of J1, A of J2, A of J3 and A of J4 in the given system. As a simple example, if I just define with respect to the previous case which we have just considered for the first part, we have defined that the R1, R2 and R3 of the given system, which are added over here, we define the R1 value as 0, R2 value in the given system is defined as -1, and R3 value is defined as minus of L in the given problem. I can consider now the similar idea for the next cases of the problem as well, and I can define this as 0, -1 and minus L in the given problem. This is corresponding to the AR1. If I go with the AJ1 contribution, we understand this given problem we need to understand. Over here we have applied the load over at this point. As we draw the free body diagram, we realize that there is a reaction over here in the horizontal direction in the negative coordinate. So, this is R1 which is -1. The vertical force in this given problem is 0. So, R2 is 0 and the moment in the given system is in the clockwise direction. So, this is minus of H. With this part we can further calculate the contribution with respect to AJ2, AJ3 and AJ4 as well in the given problem. This is the standard expression of the reaction transformation matrix in the given problem. Once we are able to identify these components of the given system, we can write the overall expressions into the two subparts as well. We can say that the one component of the given system or the action transformation matrix is associating the member components or the member action forces with respect to the redundant action forces of the system, whereas the second component is associating the member forces with respect to the joint action forces of the given system. Now, with this idea we can easily evaluate that if we have say the 1 number of redundant in the given problem and 4 number of the joint action forces in the given system, and now we are evaluating total 6 number of action forces in the given member coordinates, the size of the given B of MR could be identified with 6 number of rows and 1 number of column in the given system. So, it becomes 6 cross 1. In the same manner, if we now go with the B of MJ calculation, we understand it will have 6 number of rows because each of the member action force with respect to AM1 to AM6 will be defined, and corresponding to the AJ1 to AJ4 we have 4 number of columns in the given system. So, this size becomes 6 cross 4 in the given problem, and the overall size of the given matrix will be the size of total member action forces, which are 6, into total structural action forces in the given problem, which is 5 in the given case. So, this is a typical idea which we need to now understand to take the methods for the general matrix analysis at the later cases. In the similar manner, if we now generalize this idea, we can say that in a given problem, if the structural system is having n number of redundants in the given problem, the joint numbers are defined with the m values of the given problems. At the same time, the total number of member action forces are defined with some values of the p. Now, we can define the sizes of the individual matrices with respect to the B of MS. We define that the basic size of the B of MS should be p into m plus n or n plus m in the given system. Individually, if we go with B of m r, which is corresponding to the redundant system, the size of this matrix should be p into n in the given problem, whereas the size of B of m j in the given problem should be p cross m, which is the standard sizes of the given matrices. So, knowing this idea helps us to understand that the evaluation of the matrix is being done correctly for the given problem, and having these action transformation matrix now connects the member action forces to the structural action forces of the given system. So, as we have identified this idea, we can typically write this expression in a simplified form like this, where A of m is represented as B of ms into A of s. We can add into the two individual component of B of ms, B of mr and B of mj, and accordingly the values can be associated with respect to A of r and A of j of the given system. One must understand that individually A of r can have multiple components. It is an array containing all the redundants of the given problem. In this case, we have only one redundant, whereas AJ can also be containing multiple values with respect to all the joint action forces of the given system. Now, with this part we stop over here. We understand that somewhere we started with the member stiffness or the member flexibility in the given system. We considered that by identifying the general coordinates of the given member, we can locate the member stiffness, member flexibility in the given system. These member flexibility are defined in a more generalized form. Then there was a need that can we connect the structural action forces, which were defined both with respect to the redundants as well as the joint action forces. We considered that the structural action forces are now considered with respect to each of the member action components of the given problem, and this we did by evaluating the action transformation matrix in the given problem. And once we had the action transformation matrix, we were able to now evaluate a connection between the structural action forces and the member action forces in the given system. As a next part of our solution, we now look for the evaluation of the overall structural response, provided we have the flexibility matrix available for the member components. We have a transformation matrix which is connecting the structural system and the member system, and based upon that we can look for the solution of the overall problem. With this we stop over here. Thank you everyone.